When I discussed prevalence and incidence, we were thinking about one population, one sample, one cohort. Now we're going to expand that thinking to multiple cohorts, multiple samples, or really groups of individuals. We're going to be thinking about association. And an association is a contrast between groups which are defined by some factor. It may be, under very specific circumstances, be considered causal, but for now we're going to think about it as associations. It could, for instance, be comparing the incidence of lung cancer between smokers and non-smokers. So there we have two groups. We have smokers and non-smokers, and we're going to look and contrast those groups. Comparing survival of patients with a history of cancer versus patients without. Comparing risk of drinking among university students and the general population. So we have two different groups, or two populations. And one has been exposed, X plus, and one has not been exposed, X minus. Notice here that contrasting is necessary. If everyone smoked, then lung cancer may not have been detected as a cause or an effect of smoking. Rather, it might have been seen as something genetic. People need to be differently exposed in order for associations to be identified. And there's something deeply philosophical and fundamental about how the way our universe works. When we think about this, that associations don't exist without any contrast. I find this fascinating. I find myself thinking about this a lot, about the non-existence of things unless there's a contrast. Okay. When we seek associations, we are looking for differences between groups. That's really why we're bothered about looking at associations. We want to find differences between groups. When there's no difference between groups, we usually say that whatever measure we use takes the null value. The null value. It's a commonly used word. So if we contrast two groups with the same risk, then we expect the null value. In this group, the prevalence proportion was 50%. In this group, the prevalence proportion was 50%, and therefore we expect the null value when association is when we compare them, contrast them. Okay. This is a 2x2 table, and you should get familiar with it. It's super helpful, and we're going to use them in different sessions. And just take whatever time you need to really understand what's going on here. We have exposure and we have disease. I'm going to use X plus to mean that somebody has been exposed, X minus as somebody who has not been exposed, Y plus as somebody who has been defined as a case who has the disease, and Y minus as somebody who does not have the disease, a non-case. A is therefore the number of individuals that have been exposed and that have the disease. C is the number of individuals who have not been exposed and who have the disease. B is the number of individuals who have been exposed and do not have the disease. And D, the number of individuals who have not been exposed and do not have the disease. Counting along this line, we can say the total amount of individuals who have been exposed is A plus B. Okay? It's both of these together. And therefore, the risk of the disease is also A divided by A plus B. The number of individuals who have the disease under a certain exposure. So the risk under this exposure is A divided by A plus B. The odds is A divided by B. Okay? In this row, we have the people who have not been exposed. The same thing here. You have the total count of individuals who have not been exposed. And then the risk of disease is C divided by C plus D. And the odds is C divided by D. You have the totals, A plus C, A B plus D, and then the total of the entire cohort of everybody is A plus B plus C plus D. I said risk here because in this little session here, we're only going to care about incidence. You could do all of this for prevalence as well, but it would just be repeating myself. So we're just going to look at it from an incidence perspective. Okay? So let's start with the first measure that we have of incidence proportion difference. This is the risk difference. This is the first measure of association that we'll discuss, the risk difference. It is the difference between two incidence proportions. Recall that when I said incidence proportion before, when we defined that earlier, we called it risk. I said it was such a common term that we just say risk. So the difference between two risks is the risk difference. In our 2x2 table, it would be A divided by A plus B, this one, minus C divided by C plus D, this one. So it would be that one minus that one. That would be the risk difference. So looking at this figure here, we have a group of individuals who have been exposed. At baseline, all of them were at risk. Nobody had the disease. After 10 years, 75% of them had the disease. So the 10-year risk was 75%. They've all transitioned over that time. Among the unexposed, none of them had the factor at baseline or had the disease at baseline, and 2 of them had at the 10-year. So the 10-year risk is 50%. And so the 10-year risk difference is 0.75, 75%, minus 0.5, 50%, equals 25%. So that's the 10-year risk difference between the exposed and the non-exposed. It ranges from minus 100%, that is minus 1, to 100% positive. So from minus 1 to 1. And if there's no difference between groups, that is what I previously defined as the null value, then the risk difference is 0. You can see that for yourself here. If this one was 50% and this one was 50%, if we subtract them from each other, it's 0, right? So that's the null value is 0 in this case. So how would we communicate this? Well, we could say that the 10-year risk difference comparing exposed to unexposed was 25%. You could say something like, for every 1,000 persons who were observed to be exposed, we would expect to observe an additional 250 new cases compared to 1,000 persons not exposed over a 10-year period. This is known as attributable risk. That is, how much risk do we attribute the exposure above the normal risk? So the normal risk in this case is 50%. Whatever disease this is, the normal risk is 50%. But then the risk increases to 75%. That is, that's an increase of 25%, the risk difference. And that is attributed to the exposure. This is actually quite a neat way of communicating risk. I like it. Okay. Incidence. So that's our first measure of association, right? Okay. Now we're going to look at a second one, the risk ratio. It is, as the name implies, the ratio between two incidence proportions. So the previous one here, we subtracted one risk from another risk. Now we're dividing one risk from another risk. I apologize for these equations being broken here by line. I'm going to fix that. So hopefully when you watch this live, it doesn't look this ugly. Okay. So, but it's basically saying here we're subtracting, here we're dividing. It goes from 0 to infinity. When there's no difference between groups, the incidence proportion is 1. It's a null value. Dividing one value by itself gives 1. That's why the null value is 1. Okay. In our example here, we have a group of people who are exposed. The 10-year risk was 75%. A group of people who were not exposed, unexposed, the 10-year risk was 50%. The 10-year risk ratio is then 0.75 divided by 0.5, and that gives us 1.5. So it's like a magnitude. It tells you how much you should multiply your normal risk to get the risk in the exposed. So you could communicate this by saying then the 10-year risk ratio comparing exposed to unexposed was 1.5. Or you could say over a 10-year period, we would expect to see 1.5 times the incidence proportion of cases among exposed individuals compared to unexposed individuals. It is an asymmetric value, which you should recall this, that is asymmetric. It's important because a risk ratio of 3 may look like it's further from 1. So 1 is the null value. And 3, it looks like that's further from 1 than 0.25 is. But in fact, 0.25 means a magnitude of 1 divided by 0.25, which is 4. Okay? So because you have the risk ratio going from 0 to infinity, and the null value is 1, there's less room for the risk ratio to move between 0 and 1 than 1 and infinity. Okay? If you play around with this, this is going to make absolute sense to you. But it's something to be aware of, that the risk ratio is an asymmetric measurement. And, well, we'll discuss it later, but it could be quite misleading, the risk ratio. Okay, that's our second measurement of association. We had the risk difference. This was the risk ratio, which tries to sort of measure the magnitude of the difference. And then we have the odds ratio, the incidence odds ratio. And it is the ratio between the two odds. So you had the odds in your 2 by 2 here. We've already calculated them. It's A divided by B and C divided by D. And the odds ratio is this one divided by this one. Just like the risk ratio, it ranges from 0 to infinity. When there's no difference between the groups, the odds ratio is 1. So an odds ratio of 1 means no difference. In this case here, we have the 10-year odds is 3 in this group. And the 10-year odds is 1 in this group. And so the 10-year incidence odds ratio is 3 divided by 1. It's 3. The 10-year odds among the exposed was 3 times the 10-year odds among the unexposed. That's something you could put as a communication, in a communication paper. But it's very difficult to interpret. It's not equivalent to the risk ratio. Odds alone are quite difficult to understand. Now we're taking one odds, dividing by another odds, and then understanding what that actually means is quite difficult. Unfortunately, we end up having to use them sometimes due to statistical analysis and study limitations and so on. And so sometimes we actually need to use the odds ratios. But when you consider how many studies use the odds ratio and are forced to do so, it is a little bit unfortunate when you consider how difficult they are to understand. Okay, this here is a small toy example, but already here it's not sort of super clear what an odds ratio of 3 really means. What are the implications of that? That's why I'm a big fan of the risk difference. It's super clear. It tells you what you asked. And the risk ratio and the odds ratio, when possible, I believe we should avoid them. Sometimes we can't because they have nice statistical properties, and study limitations means that we need to use them, etc., etc. Just a quick note, if you're using the incidence rate, all of the above, you can use that incident rate, and you can use the above measures as well with the difference in the incidence rate. Incidence rate, yeah, it's actually called that. The risk ratio here, you say the incidence rate ratio here. The differences keep the unit, so it's per unit of person time. That's nice. Otherwise the rate itself is unitless, and it requires us to know the number of person times contributed. So the 2 by 2 table is really not enough to communicate those findings. You need to also somewhere mention the number of person times added observed. Otherwise, you can basically use the similar sort of techniques to represent differences in ratios, whether or not you're using the rate or the proportion.